Okay, students, we'll be starting with new topic today, binary search tree. Okay, we're going to look at the properties of binary search tree. We have already explored trees, right? In that we have seen extended trees, B trees we have seen. Now we'll look at binary search tree. So this is a tree that follows some order to arrange the elements. In a binary search tree, the value of left node must be smaller than the parent node, and the value of right node must be greater than the parent node. Now this rule is applied recursively to the left and right subtrees of the root node. So here in binary search tree, there are certain properties, or we can say we apply certain rules here, so that this tree maintains in a balanced fashion. It maintains or it balances all of its nodes according to the value of the nodes here. So every time we look for a binary search tree, you have to see that the parent node, the value of the left node is smaller than the parent node, and the value of the right node is always greater than the parent node, that is root node. And this rule is recursively applied as you proceed, as you traverse in the binary search tree. Thus, binary search tree divides all its subtrees into two segments, the left subtree and the right subtree. Now, this can be defined using the following equation. The left subtrees, that is keys, is less than the node key, that is the root key here, which is less than or equal to right subtree. Now we'll look at the representation of binary search tree. It is a collection of nodes arranged in a way where they maintain binary search tree properties. We have already seen what are the properties. Each node has a key, that is a value is associated with the key. While searching, the desired key is compared to the keys in the binary search tree. If the desired key is found, the associated value is retrieved here. Now this figure gives you a pictorial representation of binary search tree. Look at this figure carefully and just observe the values placed in every node here. You will find 27 value is placed at the root node. If you look at the left child of this root node 27, the value associated with that left child is 14. Similarly, if you look for the right child of this root node 27, the value is 35 here. If you compare both of the childs with the root node, you'll find that it follows binary search tree property. That is, left child is less than the root node and right child is greater than the root node. Similarly, if we proceed, if we come down one level next, then you can see here 14 is the root node for these two nodes, 10 and 19. Look at the values here. If you consider this 14th node, the node having 14 value, looking at its left subtree, it is left node, it is having value 10. Similarly, its right node is having value 19, which is greater than 14. If you even observe to the right subtree here, that is 35, node having value 35, then its left node, left child is having value 31, whereas right child is having value 42. So this keeps on increasing in this fashion. If you further keep on adding nodes to this binary search tree, it will maintain this property till the end. Now here is an algorithm. Step 1 states that first you need to insert the root node in the tree. You need to place the root node in the tree. Step number 2, read the next element. If the next element is smaller than the root node, insert it as the root of the left subtree and move to the next element. Step number 3, if the element is larger than the root node, then insert it as the root of the right subtree. Step number 4, repeat step 2 and 3 till no new elements to be added in the tree. Now here we have an example creating a binary search tree. Look at the data elements that we have taken here. The series says as 45, 15, 79, 90, 10, 15 and 12, 20 and 50. Now considering the first element as the root node here, we have taken 45 as the root node of this binary search tree. Now first we have created a root node. So step number 1, we followed step number 1. Now coming towards step number 2, we read out the next element. So next element in the series is 15. And we know it is less than the root node. So we will insert it to the left subtree. Then reading out the next element here, that is 79. 79 is greater than 45, that is root node. So we will insert it to the right subtree. And further proceeding to the next element is 90. So where it will be inserted? Obviously to the right side of the tree. Because it is even greater than this 79. So it will be its rightmost child. Then in the series we have data element as 10. Now 10 is less than 15, so it will be to the left side of this node. Now the next element is 55. Since 55 is less than 79, it will be placed to the left side of the node 79. The next element in the series is 12, and we know 12 is greater than 10. So we here make it to the right child of this node 10. Now proceeding in the data element series, the next element we have is 20. We have to find the appropriate place for 20. Now starting with this root node, if we proceed to the left child, it is 15. Then its leftmost child is 10, but 20 is greater than 10. Hence, we will make this 20 as the right child of this node 15th one. Similarly, the next element we have in the series is 50. Finding the appropriate place for 50 is here. Yes, can any one of you tell me? Since 50 is greater than 45, so it will be towards the right subtree. And then comparing every element in the subtree and finding the appropriate place here. So we found here 50 should be inserted to the leftmost side of this 55th node. Now there are basic operations associated with binary search tree. The first operation is insertion. Here you will be inserting elements in a tree. You'll be adding new nodes in a tree. Second operation is search. So search means you're looking for a particular data element or particular value in the binary search tree. Next operation is delete. Here you can delete any of the element in binary search tree. That will delete, that will remove the element from the tree. And the last operation is traversal. That is visiting every node in a tree.